Good morning, everybody. My talk is going to be about feature selection, and the title is up there on the screen. I'm going to do a few things today with you, and basically just going to introduce myself because I'm not rude, or at least not too much. I'm going to tell you a story that I hope you will like, and I think some of you might relate to that. And then I'm going to show you some code and some results, some numbers. I know you're all wondering, can you be any more vague? I could have, but this would be enough for today. So first things first, a little bit about myself. There's a few things going on in my life. I am a physicist. I translated into a data scientist for some reason. I work with many different types of technologies that I'm very passionate about, and that wouldn't have fit on the slide, so I just added the first few ones. And I'm a ham radio operator. Does anybody here is one? 1, 2, 3, 4, great. I'm not alone, because I usually am. And there's a few things, but this can be summed up in the fact that I'm a generic nerd, so some of you might relate to that as well. And I want to tell you first a couple of things about the company I work for. The company is called Optum. It's right there in the bottom right-hand corner. Has anybody here heard of Optum? No one? One hand. Oh, yeah, of course, it's you. Sorry, guys, he's a colleague of mine. He sits like 2 meters from me, so yeah. Anyway, let's try this again, because no one ever heard of Optum. Have you ever heard of United Health Group? No one. OK. That's a good start. No one ever has, by the way, not in Europe at least. We're part of, as Optum, we're part of United Health Group. It's a very big American corporation that works around healthcare and health services. It's actually quite a big company. We're talking about almost 300,000 people working for that. And this slide is actually a bit old because it's from last year. It says we're ranked 6th on the Fortune 500 list. That's not true anymore because we're 5th now. Yay, go us. So it's actually a pretty interesting company. And if anybody is interested in working with hardcore data science and cutting the edge in healthcare, we are hiring worldwide. So have a look. There's a couple of careers websites on both of those sites at the bottom of the slide. Anyway, back to us. The main purpose, as I mentioned earlier, is for me to tell you a story. And as many stories, as many fairy tales, this story starts with a brave white knight in a shining armor. And by the way, that white knight, it's basically all of us. It's just a metaphor. And as any good story, this story also needs a villain, because this knight in shining armor has to defeat and slay a terrible dragon. And you might be wondering, OK, we're all data scientists. We don't really fight dragons usually. Well, again, it's a metaphorical dragon. And the way it usually comes into existence is this. And I think some of you might relate to this situation. It's basically the evil overlords atop their white tower going like, we have all of this data. Let's just do something with it, even if they have no idea what to do. So what happens at this point is that you get handed your own dragon. And this usually comes in the form of a very big data set you know nothing about and you're supposed to do something with. And yes, it is that vague sometimes. This happened to me not too long ago. And it might look something like this. So you start a new project, and this video is not running. Yeah, start a new project. This happened. This actually happened. You get handed a big data set. You know nothing about it. You just know that somebody processed it in some way, and you have to do something with it. So you start by having a look at it, poking around, see what's in there. And, a few things like this might happen. You realize that the data set is huge, and you have no idea what's in there. It has over 800 features. What are they? So you just decide to have a look. What are they? And I kid you not, this happened. And there were hundreds of features like that. And I had no idea what they were. There was no data dictionary. Of course, there never is. And it goes on. there were about 200 features that had reasonable names. You could just kind of make out what they were. And then there were like 600 of these. What was the sentence? Garbage in, garbage out? Something like that. I mean, it's just too much. And I've been feeling like that for weeks while working on that project. Can anybody relate to that? Show of hands? Yeah, of course. Because the sad reality, actually the happy reality if you think about it, is the fact that of all the information, we usually need a very tiny portion of it to reach our goals, to accomplish our task. I'm not saying that everything else is definitely useless for what we're trying to do, but it's probably just adding something on top what we need to do. It's a plus, but we might not strictly need it. And of course, when you're working with such a big amount of data, such a big amount of information, there are many problems that can arise, like the fact that you have no idea what's in there. The fact that even if you do have some idea of what you're trying to do and how you're trying to do it, training time might increase, sometimes exponentially with the number of features, and you don't know which features are relevant, which features are garbage. Hardware requirements might increase because sometimes you just need to load a lot of a good chunk of the data in memory, and then you have memory constraints or CPU constraints, or if you need to go for deep learning, you might have big constraints regarding GPU availability, which are not always satisfiable. For example, in our company, we work with very sensitive data, so we are not allowed to use AWS. So if it's not in our server farm, you can't have it. That's the problem. And also there are problems like decreased performance and overfitting, because again, you don't know what features are noise and what features are relevant for your problem. And there's the risk of leaks, because again, some information regarding the target might actually leak into some of your features. And you might just be thinking, yeah, sure, but it won't happen to me. I'm really careful when I do my feature engineering. But sadly, yeah, it can happen to you. And it happened to me not too long ago. I was working on a classification project. And I spent a couple of days sifting around the data. I couldn't understand most of it. I had a fair idea what most of those features were. I did some clever feature engineering tricks, like a week or so of that. And then I trained my first model just to have a baseline. And I got an incredibly high accuracy, 99.9%. So has that happened to you? You train the first model, sky high accuracy. So of course you're like, woohoo, it's great, problem solved, for the first 2 seconds or so. Because then you're like, yeah, this doesn't sound right, this doesn't look right, there's something wrong here. And it turns out that there was something wrong. There was some small leakage from the target into one variable. And once I realized that, and once I fixed it, accuracy went back to a normal value, something that I would have expected. But this is a problem, because if the accuracy caused by that leak would have been in the order of 85, 89%, I wouldn't have been that suspicious. But the results would have still been wrong. So you should always be careful about these things. But anyway, getting back to what we're here to talk about. We're here to talk about feature selection, and we can't really work with a very big data set, and we can't really expect to tackle a big problem right here, because this is just a talk. We don't have that much time, and I'm pretty sure you don't really have that much desire to actually do that. So let's restrict the scope of this problem. Let's work with a simple data set, and that has a target. So we're working with a classification problem, and let's see what can we do about it. Full disclosure, I'm using a small data set, a public data set that probably most of you have worked on. I'm not going to tell you which it is until the end of the talk. But some of you might guess what it is. Where is my cursor? I need my cursor. Ah, there we go. And this is what the data set looks like. So we have 500 odd rows, 30 features, and these are the feature names, X00 till X29. So we have no idea what they are, and we have to deal with it. And this is a problem, because which features do we choose, and how do we choose them? This is of critical importance, because different problems demand different types of solution. And we have to be really mindful of how we choose metrics, because sometimes we use techniques or metrics that are just not relevant or plain wrong for our type of problem. This is an example of it. Are you familiar with the Anscombe quartet? Are you familiar with correlation for choosing good metrics? I bet you are. So a lot of times, we just use correlation and see if a metric is correlated with a target. And if it is, OK, it's important, let's keep it. If it's not, yeah, maybe let's drop it. But this can be a bit deceiving. In the Anscombe quartet, these are 4 famous examples of data sets that have the same summary statistics. So these 4 pairs of x's and y's have the same mean, variance, standard deviation, and regression coefficient. So it's a problem because clearly in 2 of those cases the regression, the correlation exists. In the other cases, yeah, not so much. So you can't just use. There's no technique that fits all problems. And you might be familiar with there's no free lunch theorem. Sometimes lunches are actually very expensive, not just not free. And wherever you're working with this kind of elements for feature selection, always maintain a healthy dose of skepticism. That's never wrong. But then how can we perform feature selection then? Well, there are 3 main classes of algorithms that can do that for us. And namely, these are filter methods, wrapper methods, and embedded methods. And I'm going to tell you a little bit more about those in the next few slides. Filter methods are the simplest form of it. They usually basically perform univariate analysis between features and the target, or in the features itself. For example, a clear example of that would be a variance threshold. You don't consider all features that have less than X amount of variance. And this happens all the time to me. I always get handed data sets which contain at least 10% of features that just don't change, or that are all missing. They're clearly not really useful, at least not in the way they are. Some examples of this would be techniques like F-test, ANOVA, Granger causality if you're working with time series, LDA, techniques like that. Then there are wrapper methods. These are a bit more sophisticated, and the way they work is they train subsets of features, and they look for what features are useful. So for all subset of features, you train a model, usually classification or regression, and you determine which models perform the best. So this is a bit more sophisticated than the first type of algorithms, and it's a bit prone to overfitting because you don't really have fine control over what the features do, and over what the models do. And they have a big problem. You have to train a lot of models. So if you have a small data set, these are fine, but if you have a big data set, probably not a bad idea, not the best idea. And then, as I mentioned, there are embedded methods. These try to take the best of both those worlds, of filter and wrapper methods. And the way they work, they perform a classification or a regression, but they also have their own internal way of performing feature selection. A few examples of this would be, for example, decision trees or random forest, which basically use their own internal representation of the features to determine the best splits and to determine what features are useful. And these are quite good. They're less prone to overfitting, and they usually yield good results. And they perform their search using cross-validation, usually. All right, let's close this small parenthesis, and let's try and remember why we're here. Remember the knight in shining armor? I mean, come on, we have a dragon to defeat, so we have to slay that dragon. So, and the way we're going to fight this dragon is with code. I'm going to show you a toy example, let's say, on the data set I showed you earlier. We're going to perform a small feature selection exercise using an embedded system. Sorry, an ensemble system, because we want to make things a little more spicy, more complicated. Otherwise, anybody would be able to do that. Word of advice: this code is formatted for slides and presentations, so don't just take it and use it and expect it to get correct results. I'm omitting a few things. I actually have part of this code embedded in a personal library, but there's a lot of things I'm omitting here, like validation, error handling, and so on. So take inspiration by all means, but I would advise against using it as it is. So My requirements for this type of library were that it didn't need to be a free-for-all algorithm. It had to have some guidance as to what it was supposed to do. And it had to be extensible, so you should be able to just add new selectors to the ensemble algorithms and expect it to work. And there are a few ways we can actually combine the results in the end, because we're using different feature selection techniques, and then we combine the results. So we can actually add a weighing mechanism. For example, you might want the results from a specific algorithm to be evaluated as more important than others. And that's not here, but that was the idea. So let's have a look at the code. And let's start simple. We just need to start by importing the things we need. So these would be the building blocks of the class and of the selector. And we're going to use just 5 techniques for this one because it's enough for a demo. So we're going to use random forests, decision trees, and variance threshold in flavors for classification and regression, because we might want to work in both worlds. And they do work in a slightly different way, so it's a good idea to have them separate. And then we set up our class based on the type of problem we want to tackle. So we might have a regression problem, a classification problem, or a generic problem, like when we don't have any targets, and we have to still sort out all the garbage because we don't want to deal with that. In that case, we are probably better to, we're kind of doomed to use filter methods and see what features are just not relevant. Like in this case, I'm just using variance threshold, and which has to be used kind of carefully because that has meaning only if all the features are in the same scale, especially if you're using a hard sets threshold. But this library takes care of it in the background, so we're all good for that. Then we have to initialize our class. We need to know how many variables, how many features we want to get from each of those models. We want to know, we want to set a few thresholds, like the actual library that I'm using is actually able to compare trained results, test results, compare the scores, and see if they differ by a certain amount of score. And if that happens, it raises a warning. Like if you get 90% accuracy in your training set and 20% accuracy in your test set, that's not a good sign. And you should really, review what you're doing. But again, we don't want to block results. We just want to be notified of that. Then we need to select all the models based on the analysis type. Like in this case, the analysis type keyword would identify regression, classification, other, or 2 of them anyway. And based on that, we select the models from those that are in our class. We instantiate them, and we put them somewhere safe. In this case, our somewhere safe is just alive estimators, so the ones that were chosen. By the way, if you have any questions about the code or about anything else, just raise your hand and ask. No? OK. We have our set of models in our internal object, and now we need to fit them on the data. And this is actually quite easy. We just go over all of them. We have the data, and we just fit them. Now, at this point, we have a set of models or techniques that are fitted that know about our data, and we can extract results from them. We can see what they consider as important in the data set. And the way it can be done, this is the way I did it. There's many other ways of doing it, but I basically select the relevant feature from the model itself. Some models have an attribute called feature importances, some models have variances, some models have score, and so on. For the models that I was dealing with, these were the most important ones, and I didn't need to add anything else. I get the score or the importance for each feature from each model. I combine them, and you can see at the bottom here, the last row, I only get the first n features from each model. This is specified in it, so I only want, for example, 5 features from each model. You will end up with more than 5 once you combine them, because there's no guarantee that all the results would be exactly the same set. Actually, that's quite a rare occurrence. And then we have to combine the results. And the way we combine the results is by having the models cast votes. So I have a list of models with their results and the features that they consider important with the score. And I count how many times the features appear as being identified by one of those models. Features that get more votes, so that have been chosen by more models, get a higher value. And this is where a good weighing system might come into play, because again, some models might be not that important. For a classification problem, variance threshold is probably not as good as identifying good variables as a decision tree, for example. Maybe, depends on your data, depends on your problem. But yeah, this is the basic implementation. We don't really need anything more than that. At this point, we are good to go. So let's see if it works. All right, remember our data set was those 500 odd columns, rows, 30 columns, and with those column names. We want to run our, it's really hard to see my cursor there. We want to instantiate our ensemble feature selector. We want to treat it as a generic classification problem, so we're going to use all the classifiers and all the other techniques. And we set the names of variables so that we have something more explicit than just indices. And we want to get 5 features from each model that we fit on the data set, and we get the target. Sorry, and we get the votes. And what it looks like is this. 9 features were selected, these here, and these are the number of votes they got. And you can actually go inside the library, inside the object, and examine what scores those objects got. So if you want to know how important the single features were identified by the models, here are the single scores. 5 features per model. But since each model selects 5 features, you end up with more than 5. We have 9. All right. So are you satisfied? It works. Are you satisfied? You shouldn't be. OK. It works. But does it work? I mean, does... Sorry? Exactly. It's giving me something. Is this a correct result? Is this a useful result? We don't know. Well, it works, but does it work? So what I did is I trained the same type of algorithm, which is a logistic regression. This was a binary classification. And I trained that using the whole data set first and just the subset that my ensemble has identified. And by doing that, I collected the results. And what would you expect? Better, same, worse? By how much? Come on. Better. By how much? It doesn't have to be a precise number, just twice. It's not that good. Oh, shoot. I'm sorry, I'll be a disappointment to you guys. Anyway, no. I'm using the same seed for both runs, and the model score using 9 features is actually a tad better than the model using all of the features. But again, both those scores are really high, so I couldn't expect to get 50% increase on that. Full disclosure, I've run this a few times. It's not always better, because there's a random component to it, using different seeds. But all the results that I could find were always compatible with each other within 2–3%. Sometimes it's better, sometimes it's worse. But I think the worst score I've seen using, I think it was 8 features that time, was in the range of 94–80, something like that. So still good, because...
You try just maybe use only 30 rows of data instead of 500 rows.
Yes, but why?
So this way, less feature maybe can have significantly better results. Because if you have 30 rows and 30 features, you don't have enough data.
I don't follow. Sorry, maybe find me later and we can discuss this. Anyway, as I was saying, these results are are always comparable, and it strongly depends on how the features are selected. And this is a small example. We're working with 500 rows, less than 600 rows, and with 30 features. But imagine that you could safely drop 1/3 of your data set and get comparable results. And imagine that your data set is something big, like millions of rows and thousands of features. There will be a huge speed up in your training. There will be a huge speed up in your work. And I've used this in a couple of projects, and it actually worked. How well? Well enough. I mean, I got results comparable with the ones I got without the feature selection first. But to sum up, the main important points are that you should always take care of knowing what's inside your data. You should always spend time getting to know it intimately. If you can. If you have an example like the one I showed you earlier, then good luck. You have all my sympathy. But you should always take care of selecting the features that are relevant for your problem, because you might have stuff that is really important for something else. Then you probably don't need to use that. And feature selection essentially simplifies the models because it takes the garbage out, or stuff that you're not interested in, out of the picture. And imagine that you have a very specific problem. You can build your own feature selector because you know what metric you're looking for. And you can just stick it into something like the ensemble that I've shown you and give it a very high weight, something like that. And that would help a lot. I've done that a couple of times, and it really helped me. Maybe it'll help you too. Feature selection increases generalization because, again, you get rid of noise. And if you're working especially with linear models, you don't want to have too much noise in there, especially if you have highly collinear variables, because that will throw all your coefficients off the roof, and you won't be able to use them directly, and that's a big problem. Sometimes it helps you avoid the curse of dimensionality, because, as you know, the higher the number of dimensions, the less meaningful distances become, and that's essentially what the curse of dimensionality is, and therefore it's hard to compare objects and records between one another. And in general, it removes noise and simplifies everything. And again, if you have to choose between something complex and clever and something simple and clever, you should definitely choose the simple and clever. And that would be it for me, and I'm open for questions now.
Thanks very much. Are there any questions here?
Thank you for your talk. I'm also very interested in this kind of automated machine learning, where you don't have any clue about features. It's an interesting sport. But have you looked at papers like the data science machine or H2O that kind of try to do this automatic machine learning?
I have, and personally, I prefer to work on features myself because at least I get to know the data. I mean, worst case scenario, I get to know what's in there, even if I don't really know what the feature represents. I don't trust automatic feature selection completely when it comes from the outside because I want to know what's going on under the hood. But that's one of my idiosyncrasies, so there's nothing wrong with that.
Hi, thanks for the talks. Do you have any particular class of model in which you think that feature selection is really important as compared to other ones? I don't know, linear models and compared to random forests?
So some models do perform feature selection within the implementation itself. Like if you're using random forest, you are performing feature selections before actually running the classification. That being said, some models are very sensitive to features, some models not so much. But I would say that going through the effort of doing that is a worthwhile investment of time because you get to know the data, and that's paramount in my opinion.
This I agree, but do you think there are some particular class of models in which it's incredibly important to do feature selection?
Depending on what you're trying to do, definitely for general linear models. That's one I always am very afraid to touch without having a fair understanding of the data.
Any more questions? Just down.
They're making you travel today.
Yeah.
So did you try regularization like the rich in scikit-learn, because that's usually quite okay with dealing with like a lot of variables?
Mm-hmm. Yeah, that's another technique. Actually, that kind of falls under the umbrella of being one embedded method, ridge and lasso as well, because you can use the coefficients that you get as a measure of how the variables are related to the target. And yeah, I've done that, and it's a good technique. But again, there's no free lunch, so it might work very well on some type of data and be completely off on other.
And which was the data set? Because I have my own pipeline, so I want to try, right?
All right, so what do you think that data set was? It's a famous one. No? I work in healthcare. Diabetes. There you go.
Anyone else? Can you just pass that?
Thanks for the talk, very interesting. So in machine learning, if I pre-process my data, I split it first, and then I use the same transformations from the training set on the test set.
Mm-hmm.
Do you think the same should be done for feature selection as well, that you select your features only on the training set so that leakage does not occur?
That's what I usually do. When I perform feature selection, I usually work just on my training set. And I usually have not just one test set, but I also have a validation set that I set safely away a long time before I started working on it. But that being said, you can work around this and maybe have a look at different permutations of the data set. I do that sometimes if I want to test the stability of my selection methods. But that only works with data that is not time dependent.
So it happens very often that not just a selection of features, but also a selection of rows might help. Because essentially, feature selection is eliminating features that are duplicates or near duplicates. You could also eliminate rows that are near duplicates. So you would essentially have a smaller data set that you would learn your model on without the noise. So is that something you look at as well, a training curve? It
depends. Removing duplicates from the training set, or removing duplicates is always something you should be wary of, because it's always something you should take care of, because they don't really add extra information unless you're trying to oversample for imbalanced classes. Removing almost duplicates or near duplicates, it's a bit more complex, because they might actually add information and you just don't realize that by looking at the record. Some algorithms are more sensitive to this than others. Like if you were using deep learning and you had a very deep neural network, and I would probably leave all near duplicates in, because they might have some nuances that you don't really see just by looking at it, but they might have some hidden dependencies. But if you're using, if you have 500 records and you're using a decision tree, you can safely remove duplicates.
Just continue what I asked before. Like if you have so many features, but you have very limited data, like you have 800 features, but you only have 40 rows of data, and what kind of feature selection you can do with it?
That's a very tough problem. I can't say I had to work in situations like that, so I don't know what I would do right now. But personally, I would definitely have a look, because initially at the variance, because if I have very few rows and a lot of columns, there's bound to be, hopefully, a good chunk of those features that don't really vary too much. And I would probably start by eliminating those, and after that, you kind of have to play it by ear.
Okay, thank you.
So thank you for your talk. I just want to continue the question about regularization. Did you compare that with the traditional lasso, or like your findings? And did you use regularization, like lasso regularization in your linear models after doing this initial feature selection?
So there are two things that I want to say about this. I have used lasso and ridge for feature selection in a technique like this during my work and my job. I haven't included them in this example because time. And it would have had an extra layer of complexity, because their interface is slightly different to get the coefficients. And I didn't really want to tackle that during the talk. But yeah, it's definitely something you should investigate if you're interested in it. because it works sometimes.
But did you happen to have a comparison, or did you run a comparison whether to run more, to have this voting system versus just using Lasso and say, okay, this voting system works better, or it's just something that you wanted to have more control and you decided to?
No, I haven't run a comparison strictly like that. Although I have used results from Lasso within algorithms like this, so I didn't really need to compare those results with the final one. But yeah.
Thanks. Anyone else? Can't see anyone. Wave if you have a question. No?
All right.
Okay. Well, can we thank our speaker again?
Thank you all.